All right, let's continue our conversation in sustainable energy studies by focusing now on that second word, energy. We've discussed sustainability and environmentalism, environmental issues, some general principles of ecology. And now let's take a look at energy, what it means, and what we typically think of when we talk about energy and how it relates to the human environment and how it relates to the natural environment. So here we go with an overview of energy as related to sustainability. And we're going to dive into the finer details of electricity generation, renewable, non-renewable, things like that. But before we do, I like to sit and think about what is energy and why do we think of it the way we do. So of course, the background image here is of the sun, and we use that as kind of our reference point for energy on Earth, because ultimately, all of life as we know it is driven by the energy of the sun. So you are alive because you eat food. That food is grown with the energy of the sun. And almost all of our electricity, even for our modern way of life, relies on energy from the sun. You might say, well, I don't see solar panels everywhere. I know that there's a power plant down the road and it burns some kind of fossil fuel. So that's not solar power, is it? Well, you think about it, and if it's coming from a fossil fuel source, that means it was once alive, and then it one time relied on the energy of the very same sun. So it's kind of a stored form of solar energy. Whether it's coal, oil, natural gas, it all comes from ancient living things. They all relied on energy. Well, how about wind? How about hydroelectric power? Is that related to solar energy? Yes, it is. Because why do we have wind on Earth? It's because the heat of the sun creates pressure differences, which allows the windmills to turn. And similarly with the water cycle, it's all based off of evaporation, which is done under the energy of the sun. So pretty much everything is a solar energy source. The only exceptions would be geothermal, something that relies on the heat that's generated inside of the Earth, or nuclear power. But as far as we generally think of it, we're a predominantly solar-powered system. So let's discuss what is energy in the first place. Before we talk about electricity and some of these other things, we need to remember that energy is different. It's its own special thing. And all we mean when we talk about energy from a scientific or a physical perspective is the ability to produce change or do work. So if you want to change something, technically that's doing work, and that requires energy. There's many forms of energy, and there's many ways to do work. So what is work from a scientific perspective? Work is, there's a formula, work is force multiplied by displacement. Now, displacement is kind of like distance, although it could be thought of better as the useful distance. If you took a shortcut, that's what really matters. That's the displacement. So if I have an object on my desk, I want to pick that object up and put it some other place, I have to do work. And in order to do the work requires energy. So the work is measured in joules. That's the unit that we use to measure the energy required to do the work. So if we kind of break it down a little further, what is force? Well, force, if you recall from, I don't know, maybe 7th grade or into early years of high school, the force is the mass, kind of like the weight of something, multiplied by the acceleration. Okay, so now we're thinking about how heavy something is and how much it accelerates and how far it goes. What's the acceleration? Well, the acceleration is simply the change in velocity compared to the change in time. So here we get kind of all of our basic variables of energy and why we need to do work. If the item we are moving is heavier, it will require more energy. If we want to move it more quickly, it will require more energy. If we want to do that in less time, it will require more energy. And if we want to move it further, it will require more energy. Before we discuss the magic of turning on the light switch and having the lights turn on, it's important to just remember when we discuss sustainable energy, we bring it back to the fundamentals. We're in principle talking about moving things of various size over various distance over various times. Now there are two primary types of energy. And again, this goes back to the elementary discussions of physics and science. We have potential energy and kinetic energy. So potential energy, they call stored energy. That would be the image on the left-hand side. You can see the ball is at the top of the hill. How did it get to the top of the hill? Well, something had to put it up there. It required energy to move that ball to the top of the hill. And then the kinetic energy is when the ball is rolling down the hill. And what is the force that's causing the ball to roll down the hill? The force of gravity is creating that. So we have a gravitational energy that is pulling the ball down the hill. So while the ball is in the stored form, we've got the potential energy locked up, kind of like a battery ready to go. And then when it's released, then work can be done and the ball is moved down the hill. It would require more work to move the ball back up the hill again. Thinking in terms of potential and kinetic energy is significant when we discuss useful forms of energy for human life, because we can break down our known types of fuels and energy sources based on their various potential versus kinetic resources. Remember, potential is like stored energy. And so the ability to store energy for later use is very important in our modern world. So what are the various forms of that stored or potential energy? Well, we have chemical energy. For example, oil, gasoline, fossil fuels are a form of stored energy, chemical energy. We have elastic energy, like a rubber band or like a balloon, you could say, something that's stretched and ready to release that energy. Nuclear energy is stored in the form of the uranium molecule, which is very heavy and gives off radiation over time. We'll discuss that in slightly more detail today, but in greater detail in future lectures. And then there's gravitational energy, which is the example of the ball at the top of the hill. It's also the example of water stored in a lake or reservoir, especially if there's a hydroelectric power plant at the dam that's holding back the reservoir. So that's all energy that could be used later. Then there's kinetic energy. The kinetic energy is the energy that's in motion currently. And so there's electrical energy. There's the electrons that flow through a wire to create electrical energy. There's radiant and thermal energy. Both of those have to do with how heat is transferred, either conducted or radiated through space. There's motion energy. Anything in motion has a form of energy behind it. And then there's sound energy, which is a kind of interesting one because sound is a physical thing. There's compression in the air, and our ears pick that up as sound, but a microphone also could pick that up with the various forms of movement in the air. So kinetic is movement, and stored is potential, and we use all forms of energy for our modern way of life. Now, if you want to be an innovator or come up with some solution, you can help to think creatively about how we might use a new or novel form of either potential or kinetic energy to solve a particular problem. So let's continue with our introductory lesson here by looking at the first law of thermodynamics, otherwise known as the law of conservation of energy. And that law states simply that energy can be transformed from one form to another. It can go from potential to kinetic, and then back to potential, and on and on. It's always changing forms. But it cannot be created, nor can it be destroyed. There's a finite amount of energy in the universe. So if you want to add energy to a thing, you have to take that energy from another place or another form. If you're going to pick up a box, you're going to use energy. You didn't make that energy. You transformed that energy from the food you ate. And that food was a form of energy that came from another source. So we're always just shifting energy sources and forms around. We're not creating or destroying. We're not losing ever any actual energy. Now, when we apply that concept to a system, and a human is a system, or a society is a system, or the planet can be considered a system, the energy will pass from various forms. It can do work. It can give off heat, often as a byproduct. It can be trapped within matter, and it will go into and out of the system. That system's internal energy will change in accordance with the law of conservation of energy. So, as I said before, you are not creating energy. You are simply having energy come into you in the form of your food. You transform that energy into ATP, and you use that to do the work of metabolism. And you also give off heat and a few other things as waste products, byproducts, and there's energy involved in all of that. So if you're looking at yourself as a system, there's energy in, energy out, and energy within. And it's the same for our system of living. It's the same for our planet. We have energy coming in, we have energy going out, and we have energy that sticks around for a while and changes various forms. And all we're doing when we discuss sustainable energy is trying to manage the way that that energy changes forms so that it doesn't cause problems for humanity and other living things. Another piece to the first law of thermodynamics is that a perpetual motion machine, or any kind of machine that will produce work without the input of energy, is impossible, because you always are going to lose some energy as friction, as heat, and so you're always going to need to continually reapply energy in order to do work. So this is important. A lot of folks like to sit around and daydream about, okay, if I could just think of the most perfect way to spin something around so that the weight picks up the other side, you think, okay, I've come upon the solution, which is just free and unlimited energy. Well, that's impossible. Sometimes you'll see people present themselves as having invented a perpetual motion machine, and you can see an image here. That's something you could buy on Amazon even, that kind of shows a ball rolls down a hole, goes on a track, jumps through the sky, and goes back into the same platform so that it can keep going in a forever never-ending circle. And if you look closely at any of these attempts to call themselves perpetual motion machines, you will see that there's always some kind of hidden energy source. So in this case, there's obviously a little plug that you plug it into the wall in order to create maybe a magnet or something that pulls that ball down a little bit stronger so that it has enough force to make it back up to the top. There could also be batteries in there or some kind of sneaky thing going on. But don't be fooled. As far as we know, perpetual motion machines are impossible. So we're always going to need to add more energy in order to continue doing work. So how do we use energy in our modern world? Most of the time we think about electricity when we discuss energy. And because electricity is a very useful form of energy, it's kind of transferable to a lot of things. We can run all sorts of things, light, sound, movement with the electric energy. And so at the center of nearly all power stations is a generator. A generator is simply a machine that will convert mechanical power into electrical power, mechanical energy into electrical energy. We tend to think of the mechanical source as the primary form of power and the electrical source as the secondary form of power. And the way a generator works is you use movement, mechanical movement, to spin a conductor between a magnetic field. The conductor is usually a coil of wire. Metal is a good conductor of electricity, and if you spin it around a magnet, then you can cause the electrons in that metal to move along the wire. And so you need some form of movement in the first place to cause the thing to spin around. And once you can harness movement, then you can have a coil of wire spinning around a magnet, or a magnet spinning around a coil of wire, same thing. And once you do, you have the ability to cause electrons to move along the wire in the form of a current, and that can do work. Now, there are forms of energy that we consider to be renewable, and there are some that we consider to be non-renewable. Renewable energy is anything that can replace itself on a human time scale. Oftentimes we think of within like 100 years or within a human lifespan. Some things are rapidly renewable, meaning like within 10 years, it will come back. Think of like trees. You chop down a tree, maybe bamboo, you cut it down, you burn the bamboo for energy. In 10 years, that bamboo has grown again with the energy of the sun. And then there are things that are non-renewable, things that won't replace themselves over a meaningful time period for humans. So it's kind of like we get one shot, one opportunity to use this energy, and then it's gone. This would be like the coal and the oil. So let's take a look one by one at these various forms of energy. We've got solar energy, geothermal energy, wind energy, biomass energy, hydropower. Those are all renewable forms of energy. And then we have petroleum products, hydrocarbon gas liquids, natural gas, coal, and nuclear energy. And those would be things we would call non-renewable forms of energy. It doesn't necessarily mean one is better than the other, but in terms of how we sustain the reaction, the mechanical energy that generates our electricity, some are going to renew themselves on a human time scale, and some we kind of use it and then lose it. Now, the nuclear is a little bit of a special category, which we'll discuss in greater detail in a moment. But let's take a look at how the United States uses energy by various energy sources. So we can look at this pie chart and we can see that if we were to break down the renewable versus the non-renewable energy, as of 2021, renewable energy made up only 12% of the energy consumed in the United States. The rest of it was all non-renewable energy. Non-renewable energy is mainly the petroleum or the oil, the natural gas, nuclear, and coal power. You can see the pie chart breaks down the renewable energy into geothermal, solar, hydroelectric, wind, and biomass. So you can see the various ways that the United States currently consumes renewable energy versus its non-renewable energy. But how does that pie chart look as we compare it over time? So if we look at energy consumption by major sources from 1950 to 2021, we can see that a number of things have taken place. Notice that the overall amount of energy consumed has grown since 1950, but it also has kind of leveled off since 2000. Now, this is not the energy that we produce. We produce more energy now than ever, but this is the energy consumed. So there's a difference between making energy, generating electricity, and consuming electricity. So we've kind of leveled off in our consumption. And what other things do you notice? Well, most obvious to me is that the lowest item, coal, the dark blue color, has dropped significantly. It peaked around 2000 or 2005, and since then, coal as a form of energy that we consume has dropped. And natural gas seems to have grown a bit. Petroleum seems to have stayed the same. And we can see nuclear kind of started in the 70s and it grew. It has stayed relatively constant for the past 20 years. And renewables has slowly grown over time and it continues to grow. So it's almost as if the loss of reduction in coal generation has been made up with the increase in renewables. And you can see we've got kind of these dynamics that change over time. Now let's take a look at each one of these energy sources and look at their primary and secondary generation capabilities and just kind of talk about them one by one and see how relevant they are to our world. So first up, let's talk about the renewable energy sources and let's focus on solar because that's the one most people think about. Solar panels are the way to go for sustainable energy. And before we even think about solar panels, remember those are generating electricity. So that would be a secondary form. We also consider the primary form of how we might use solar energy in our modern world. One example would be solar hot water heating. So in a residential or commercial application, the heat from the sun can heat water. That water can now be the hot water used in the home, or that hot water could also help to regulate the temperature of the home. In a secondary source, the photons from the sun can be converted in a simple yet sophisticated way to generate electricity, and we'll learn more about that in a couple weeks. Next up, let's take a look at geothermal from a primary source. Again, we can use the heat of the earth to regulate the temperature inside of a building or in any other sort of method. Anytime there's hot and cold, you can use that to create a circulation and create that to do work. Similarly, the heat from the earth can generate steam, which can turn a turbine, which can make a spin that causes electricity to be generated. So we can use geothermal energy to create electricity at a power plant. Now we've got wind. So wind has been used by people for a long time. Think about sailboats. That's using wind energy to move a ship across the ocean. And there's even some attempts to bring back sails to the shipping industry, either in the form of a large sail or a kite that you fly up in the sky in the optimal conditions. And maybe you keep your boat engine, but just fly the sails so that you need to use less fuel, kind of an assistance. So we've got primary forms of wind energy, even windmills that are used to pump water, or windmills that are used in a mill to grind grain in a traditional setting. Those would be a primary source of energy. And then again, we can use that movement in a wind turbine where the windmill spins around, and that causes the spinning motion in any kind of, just like all the others, to turn a generator, which creates electricity. And then we've got biomass. So biomass is usually wood, but it's any kind of living thing that is burned usually. And you could burn the wood to generate heat, to heat your house or to cook your food. You can have charcoal, which is a form of biomass. And then you can take that same biomass, burn it in a boiler, and cause that to create steam, which turns a turbine, which generates electricity, primary and secondary power. And similarly, we have hydropower. So you can have a water mill. The wheel will rotate as water flows, usually like on a stream. The movement of water down a river can spin a wheel. That wheel could go directly to a factory and run the whole factory on the movement of water in the river. That was kind of the beginning of factories in our world, was water-powered factories. You can also use that to pump water. If you have the spinning motion, you can create pressure with air and water, and you can pump water with a water wheel. And now in modern times, we often will hold back water in a reservoir. We'll reserve the water behind a dam, and that dam can release water in a controlled fashion in a way that allows the movement of water with the energy of gravity to spin a turbine and then cause the generator to spin, which once again creates electricity. And now let's take a look at the non-renewable forms of energy. Those are things we call fossil fuels. Fossil because we typically obtain them from old things. So it's not actually that fossils themselves, like dinosaur fossils, are the things with the oil inside, but it has to come from a long time ago, and it has to have come from a living thing. So that is why we called it a fossil fuel. It's a natural fuel, such as coal or gas, that was formed in the geological past from the remains of living organisms. And primarily we think of coal, oil, and natural gas. So coal is a combustible black sedimentary rock composed primarily of carbon, and it is the largest source of energy for the generation of electricity worldwide. You can see the map on the right-hand side shows the major coal deposits in the world, and we can see what parts of Earth generally contain the most coal. And then the graphic on the left-hand side illustrates how coal is formed. So there's an ancient ecosystem. Usually we think of it as land plants, things like ferns and trees and peat, which is kind of a soil that is comprised predominantly of old, non-decomposed plant material. And if you wait enough time, and if you expose it to enough pressure, like pushing it down under the weight of all the land on top of it, you will have the material eventually turn into coal. So when we burn coal, we are burning the compressed ancient forms of life that used to be there on Earth. That's why it's fossil. You can never get it back once you burn it, because you can't go back in time and have created more habitat. The only way to get more coal is to wait a long, long, long time for our current land plants to kind of break down and turn back into new coal. And then we have oil and natural gas. These are similar to coal. Oftentimes, these are from marine or ocean-based organisms. And in the ocean, there's a continuous fall of dead organisms down to the bottom of the ocean, the sea floor. Whenever living things die in the ocean, that's where they go. They sink down to the bottom. There's actually a scientific term for that. It's called marine snow. The vast majority of organisms are tiny, single-celled, even microscopic organisms. And as they die, they go through their life cycle, they fall to the bottom. And so there's just a constant rate of organisms being deposited on the sea floor. They call that marine snow because it falls kind of like snow. And then given enough time and the right conditions, that geologically will become covered up and compressed. So you give time, you give heat and pressure, and now we've got oil and natural gas. There's oil and natural gas that comes out of the land as well. But remember that over time, the oceans have changed, geology has changed, and things used to be underwater that are no longer underwater. In fact, if you go to the top of Mount Everest, the tallest mountain on the earth, you can find fossils that were in the ocean. Seashells can be found up at the top of Mount Everest because that land was at one point under the ocean and then was risen up by the movement of plate tectonics. So the oil can be found all over the earth, but it's generally the result of ancient living things that died and were compressed over time. Natural gas is related to oil, and it's a relatively newly abundant resource that humans have had the ability to harness. Similar to oil, it's drilled out of the ground, and especially with modern technology, we can use something called hydraulic fracturing to have access to the natural gas that was previously unavailable. And part of the energy abundance currently in the United States is a result of its wealth of natural gas deposits. For a long time, the gas was there. It was trapped in the rock. Porous rock, like shale, contained natural gas trapped in it, but humans lacked the technology to be able to obtain it. And hydraulic fracturing technology enables causing cracks and fissures down in those rocks, which allows the gas to be released and captured and then used as a fuel source. And this is what we mean by the term fracking, hydraulic fracturing. There's some criticisms from an environmental perspective on fracking and some of the waste product and the pollution that can be a result. But before we discuss that, we're just reviewing the general forms of energy here. And then we have nuclear energy. Now, nuclear energy is not coming from a previously living thing, and its renewability is kind of debatable. Now, this becomes a very complex subject, but in general, the way nuclear energy is produced is with uranium. Uranium is the heaviest, meaning the largest, naturally occurring molecule on Earth. And so it has the most number of protons and neutrons and electrons in that atom. When we find uranium deposits on Earth, it's quite heavy. which makes it hard, dense, strong material. It is so heavy, it is right on the edge of being too heavy to even hold itself together. And so what happens is it is constantly giving off radiation. It is radiating parts of the atom out and away from the physical atom. And so what you have happening is a constant giving off of atomic particles. Now, if a uranium atom gets hit by another uranium atom, then it will have the tendency to break apart into two different atoms. And when it breaks apart, it has the characteristic of giving off 3 more atomic particles. So if we could find enough uranium and enrich that uranium to be more concentrated, then when it gives off those atomic particles, they will have a high likelihood of hitting more uranium atoms. And if you have a concentrated enough source, an enriched enough source of uranium, you can have a sustained reaction. And the sustained reaction is what is used for generating heat, which then generates electricity in a nuclear power plant. If you could enrich the uranium even more so that there's more percentage of uranium in the material, then when it gives off those 3, it's going to be much more likely to hit more uranium. You'll have a much more rapid reaction. You'll reach a critical mass that can cause a rapidly, exponentially growing chain reaction. That's a nuclear explosion in a nuclear bomb, an atomic bomb. And so nuclear is quite a unique form of energy. Now, where did this energy come from in the first place? Well, it sort of came from the sun when the sun exploded, and then when the earth formed, and it comprised all its various ranges of elements that exist naturally on Earth. Uranium is the biggest one that's there. And so we're not going to get a new explosion. We're not going to get a new generation of Earth. We're not going to get more uranium over time. And we can deplete the uranium so that it no longer produces the amount of energy that we want. So in that regard, it's a non-renewable resource. But some people are big champions and advocates because this gives off no CO2. So it's a carbon-free form of energy, and therefore worth considering if our goal is to limit carbon emissions. I also mentioned the dangers potentially of nuclear weapons, and then the problems of nuclear waste, which will continue to give off radiation, which can have health effects for people and for the environment. And so there's some technical challenges to overcome, and there's some inherent risks that come with nuclear energy that would not come with other forms of energy. However, it is carbon neutral in a certain sense, and it produces electricity for humans in a way that many would consider to be an essential solution to our climate change issues currently. What we see here is a chart showing the estimated US energy consumption in 2021, broken down by energy source, and then applied to various sectors. So you can see the different colors represent the different forms of energy. The thicknesses of the lines kind of represent the quantity, and then the squares, the boxes that they go to, represent the different uses of energy. So it's a very valuable graph to kind of grasp how it's all being transformed in our modern world. Now take a look at that first orange box right in the middle, electricity generation. It's quite a large portion of our energy consumed, and we generate electricity with solar power, with nuclear power, hydropower, wind power, geothermal power, natural gas, coal, biomass, and petroleum. All of those go to generate electricity. In the US, the largest forms of electricity generation are coal, natural gas, and nuclear, with wind, hydro, and solar making up kind of a minority of the electricity generation. Geothermal, biomass, and petroleum are trace amounts only. Let's continue the line out of the electricity generation box. Of that electricity generated, a lot of it is lost as waste, heat, transmission lines, or inefficiencies in our system. That's the rejected energy box up on the right-hand side. But then the yellow color, the lines, they get distributed out to various sectors: residential, commercial, industrial, and transportation. And the transportation would be things like electric cars. So notice how thin the line is compared to the rest. So that's just for electricity generation, but let's compare the other forms of direct energy now. Let's go back to the left-hand side and notice that for natural gas, not only does the line go up to electricity generation, it also goes down directly to the various sectors. And that is when we burn natural gas to heat the homes, to heat water, to run gas appliances and things like that. And you can see how it is applied to residential, commercial, industrial, and transportation. And now finally, let's direct our attention to petroleum. That's oil and gasoline. And the vast majority of that, as you can see, goes directly to transportation. And so that's our gasoline-powered vehicles, our diesel-powered vehicles, and industrial things like gas or diesel-powered generators that run factories. A lot of times things have a backup gas-powered generator. So now we'll direct our attention at those pink boxes and notice how different the sizes are. So residential is 11.7, commercial is 9, industrial is double that, 26, and so is transportation, 26.9. And even of those, we have some energy sources which are given off as waste product. So there's rejected energy, there's waste energy that's not used, and then only some of that goes toward energy services down on the right-hand side. So you can see that a vast majority of the energy that is produced is not consumed, and only a small amount of it actually goes toward energy services. So if we wanted to make a change in this overall system, we could try to adjust the left-hand side. We could try to change the portfolio from which we generate our electricity and use our energy. We could try to adjust the pink boxes. So maybe look for efficiencies or new forms of energy in these various sectors. Or we could look to create efficiencies overall and overall lose less energy to the environment, to waste, to heat, and to overall inefficiencies. So there's a lot of opportunities here to intervene in our system and to try to make improvements. So there we go with just an overview of the concept of sustainable energy, and then how we think of it as applied to energy useful for humans, both in a primary and a secondary form, the concepts of renewable versus non-renewable energy, and then finally, the portfolio or the breakdown of renewable versus non-renewable, primary versus secondary energy, and the sectors from which the energy is consumed. And ultimately, the amount of waste in every step of the process where we have opportunities to improve, to make things more efficient, but maybe even to consume less overall, and to try to find some kind of way of life that we can end up calling sustainable, because it's going to rely on only renewable sources by definition. Unless we find a renewable way of life, we will never find sustainability. And it's in the name. If it's not sustainable, it's not going to continue. And when we discuss sustainable energy, that's ultimately what we're talking about. How do we find a way of living that uses energy in a form that's going to enable the future to continue using energy for themselves? I hope you enjoyed this topic, and this gives us much to discuss in weeks to come.